Welcome to episode 254 of CppCast, the first podcast for C++ developers by C++ developers. I'm your host, Rob Irving, joined by my co-host, Jason Turner. Jason, how you doing today?
I'm okay, Rob. I just got the email telling me that I am approved for a 2021 MVP.
Oh, did you?
Like,
Congratulations.
literally just this moment. So I think that's year 5 for me now, something like that.
Very cool. I don't think I've gotten mine yet, but yeah, I know those emails are going out today.
I forgot that today was the day, in fact.
Okay, well, a tough episode, I'd like to read a piece of feedback. This week, we had a lot of good feedback on last week's episode with Tara Walker. We got this one comment on Reddit saying, it's really encouraging to listen to someone this passionate about their work. Would be cool if they made an IoT library for CPP SDK as well. And I thought that there were both C++ and C SDKs that we talked about last week.
I
But
thought
maybe
so
it is a pure
too.
C SDK?
Maybe
Yeah.
it is, but it works with C++.
Yeah, obviously you can use it with C++. Yeah. Well, we'd love to hear your thoughts about the show. You can always reach out to us on Facebook, Twitter, or email us at feedback@cppcast.com. And don't forget to leave us a review on iTunes or subscribe on YouTube. Joining us today is Michael Wong. Michael is the Vice President of Research and Development at CodePlay Software. He is now a member of the Open Consortium group known as Khronos, Misra, and Autosar, and is chair of the Khronos C++ Heterogeneous Programming Language SYCL, used for GPU dispatch and native modern C++, OpenCL, as well as guiding the research and development teams of Compute Suite, Compute Aorta, Compute CPP. For 20 years, he was the Senior Technical Strategy Architect for IBM compilers. He is the Canadian head of delegation to the ISO C++ standard and a past CEO of Openmp. He is also a founding member of the ISO C++ Directions Group and a director and VP of ISO CPP.org and chair of all programming languages for Canada's Standard Council. He also participates in ISO SC42 on AI and machine learning. He has so many titles, it's a wonder he can get anything done. Michael, welcome to the show.
Thank you. I'm glad you were able to read that without taking a breath. That's pretty amazing.
And that's a modified version of your full bio that's on your website. There's a lot more that could be mentioned.
Well
Wow.
done. Well done. My hat's off to you, sir.
So if you don't mind, we were talking about this just for a few minutes before we got started, but with all of those hats you wear, you're used to normally traveling like 5 weeks a month, right?
If I could, I probably would end up doing that, yes. There's a lot of committees I'm part of, but my first love has always been C++. Coming out of my experience in C++, I've been asked or prodded to join and lead other groups and other committees. And I think that's helped, that cross-pollination between different committees, because many committees often go through similar problems. And it was very useful helping each other, from Openmp to C++, now from C++ to Khronos under the SYCL working group. And then from there, I'm now actually on 3 other ISO committees, one on machine learning and AI. You didn't know that there was a committee for that. Well, yes, there is. And these guys are just talking feverishly, having daily meetings now because of the lockdown. And the other one is about safety, which is my other huge research goal. And trying to drive for more safety in autonomous vehicles. So there's a big group right now of all the top safety engineers of the world, people from General Motors, Bosch, a totally different area of my previous life that are constantly online talking about how to make self-driving cars safe.
Wow. So are you like just literally in meetings all the time right now?
I'm often because of the lockdown, I'm actually working 3 times harder.
Right.
Lockdown will be over soon, so I can work less. Because at least when I'm in an airport or in a lounge in a hotel, I can avoid calling into a meeting. I have a good excuse. I'm traveling. Right. But now I'm on call 7-8 hours a day, often triple booked. So I have a setup here in my house where I have 3 computers, 3 screens, and 3 cameras, and 3 speakers. And often there are 3 voices talking in my ear with my Bluetooth headset, depending on what I'm actually. So it's become quite fun juggling all these things at the same time. I just got off another call so I could focus totally on you guys. So wow. I'm totally not on any other call right now. I'll have you guys know. I'm only on your call.
Okay, that's good to know you're not double or tripling up podcast interviews.
I was tempted because the other call was getting into an interesting area, and their call was on Misra. which is one of the safety standards that has to do with making C++ safe. And they were on their face-to-face meeting, or their so-called virtual face-to-face meeting today, which started at 5 a.m. this morning Eastern time.
Wow.
But it was going to end anyway by about 2 p.m., which is roughly 7 p.m. in the UK, because they're following UK times. So, but I'm used to that. Ever since I joined CodePlay, I kind of live British times. I'm generally up at 5 a.m. in the morning, because that's when my office wakes up and people start going in. And by 1 or 2 p.m., things are slowing down, and then I stop for a moment before I choose whether I should continue working or go out and play some tennis.
That actually, yeah, that's about the best you could possibly get, huh? Eastern North America to UK is only 5 hours difference.
You got it. Yeah, Jason, you must know this stuff by heart. Yeah, you got it exactly right. There's a period of time you can get a lot of things done for Europe, UK, right?
Yeah,
early in the morning, and then before the West Coast wakes up. And when the West Coast wakes up, they always demand time starting around noon to later on day, right? So there's a brief period of time when I can actually do real things before all the calls ramp up again. And ISO calls nowadays are they just given up at trying to make it work for any one person. There would now be calls at 1 a.m., 3 a.m., 5 a.m. in the morning, because sometimes they have to favor Asian times.
yeah, right.
So, I'd be in bed with my Bluetooth headset. My wife would be sleeping beside me, and I'd be listening to a call coming out of Japan somewhere.
Although
I
you're
did that with SG14 last month. What I did with SG14 was I inverted our regular call from being 2 p.m. Eastern time to 2 a.m. Eastern time, so that it would be like 2 p.m. in New Zealand. We wanted to make sure that we could get our New Zealand friends and our Australian friends on SG14 on the call at least once, so that they could be comfortable, because they have never been able to call into SG14.
Oh, wow.
All the ISO call tends to be very European, US centric, as you guys know, right?
Yeah. Right. So I am curious, though, if you don't mind, you said that there's a lot of valuable cross-pollination, and I'm thinking like MISRA. I mean, we've had other people on the show that have talked about like MISRA and safety standards, and I'm just kind of curious if there's anything specific you could point to where you see like an overlap between Kronos and MISRA, because they feel like completely different topics.
They are, but they are not anymore in our world. You could also say C++ to some extent is not about safety, because it's performance. It generally could be more about performance and portability. But our world is definitely merging. A lot of workloads out there are now merging in terms of performance, being portable, but also needing to be safe, because they're getting into consumer hands. What is a self-driving car but a supercomputer on wheel? Doing very high performance stuff, potentially on portable things, on portable devices, at least when you get away from Tesla type stuff, because people want to have things that can be reused the next year instead of rebuilding it from the ground up. So speaking about Kronos and MISRA, what's going on is a lot of Kronos standards are being tested with MISRA. So Kronos things like Kronos Vulkan has a safety critical group, and what they do is they take the Vulkan API and run it through MISRA, get all the warnings and the defects that comes out of MISRA on it, and then refix the API so that it can make Vulkan safe. They do that with OpenGL. We plan to do that with OpenCL. SYCL plans to build such a thing so that it can be appropriately used in a self-driving car. So this is why there's now tighter and tighter integration between the groups. Kronos is using MISRA. C++ in some domains is definitely interested in having MISRA. We actually have MISRA coming to C++ standard meetings, attending SG12, which is the vulnerabilities optimization group. And we cross-pollinate the two groups so that, there's a new MISRA rule we want to check with C++ to see that the experts agree that this is a good rule. Have we missed something? Do we not know about something about template, argument type deductions that we didn't know about that we should protect against? Or the opposite, which is are we protecting too much? One of the big complaints in the past about Misra is it's too blanket in its restrictions. Don't use templates. Don't use exceptions. Well, that's just not going to fly in modern C++, right? And it's not flying with self-driving cars either. They're not saying that you should never allocate dynamic memory. They're saying you should not allocate dynamic memory after the car starts up. And when you could allocate as much as you want before the car starts up, but after the car starts up, you can still allocate dynamic memory, but you have to make sure that it doesn't throw an exception. You have to make sure that it's got enough space. It doesn't fragment so that it can be deterministic, so that you don't get a 10-second breaking warning when the requirement from the law is that it has to be like 2 microseconds, right? So these are very, very tightly connected fields that needs those cross-pollination of ideas. It needs the experts who are the safety experts, but it also needs the experts who are C++ experts, who are the heterogeneous experts, who are the concurrency experts. Yes, the world is definitely converging now.
That is very interesting. Now, I apologize for the sake of our listeners because I definitely skipped ahead. We haven't gotten to the news yet. And some of these things like Misra and Kronos, we definitely will have to come back and make sure we define them so that our listeners know what we're talking about.
Right. So let's quickly get through the news. And then, Michael, feel free to comment on any of these, and we'll start talking more about SYCL and your work in ISO and maybe more about Misra and Kronos. Sound good?
Sounds good.
Okay, so this first one is an announcement that GCC 11, I believe, is going to now target C++ 17 as its default dialect, which is great news.
About time, yes. Thank you. That's important. It's not easy for them to do it. I can imagine. I was very close to following GCC when I was the XL compiler lead, and I had to make sure that I had to duplicate almost every GCC feature back then. Everything, pretty much, because they were back then before Clang. They were the 800-pound gorilla, and you had to follow them very closely. Right. And it was painful for them to switch to C++ 11 because C++ 11 broke binary compatibility with SSO, and so the transition but since then they've learned, and so the transition to 14 was very quick. And 17, it was much quicker. But now we're now also talking about that the support build is also built with 17, right?
Right.
Yeah. And they did point out they are still missing 2 C++ 17 library features, but said they're not going to let that hold them up, which is good.
Oh, okay.
Yeah, to be honest, it was actually, one of them was one I didn't even know existed, and I thought that I had covered almost every C++ 17 feature on my YouTube channel.
Which one
is that?
The standard hardware constructive, destructive
interference. Yeah.
What is that?
That's actually a little known C++ feature we put in, and it's actually really important in parallel programming. When I was the CEO of Openmp, one of the biggest problems with parallel programming is fault sharing. Okay, so this is the idea where you have a cache line, and you touch the cache line with one thread, and then a different thread. Now, because of the locality, because it's so close, a different thread might keep pinging that cache line, and now you now unnecessarily thinking that the next byte that you need to access is actually on that same cache line, but it's not.
Okay.
So what this does is it gives you the ability to create a distance of separation, so to know that this is the size of the cache line. That's called the destructive interference. It means that you won't need to ping this cache line for the next byte because it's not anywhere close to it. Okay. The opposite is called constructive interference, where it is actually on that cache line, and you actually want it to be in that. You actually don't mind it pinging that particular cache line over and over again. So yeah, it is actually really important, but it's a very rarely known. I actually use that with many of my talks as an opening to let people know, hey, did you guys know that C++ 17 now supports fault sharing or restricting fault sharing?
Or at least, well, theoretically, if GCC doesn't support it yet, then...
Right.
True.
Yeah. Well, I just had this conversation about fault sharing with someone the other day, so I believe they listened to the podcast. And
yeah, if you are involved anywhere with parallel programming, that has always been a problem. With every single parallel language, not just Openmp, every single parallel language, and now C++ 11 has introduced parallelism and concurrency, has this exact issue. You just it's not a huge problem to get around. You just have to have a way to get around it. Before this, in order to get around it, you probably have to use the vendor hardware. The vendor will sometimes give you some way of getting around that fault sharing because they know the cache size of their hardware. So it was kind of just vendor specific always. So you have to use a different one for every machine, from IBM to ARM to whatever to Intel. But now this gives you a standard way of doing it, and you don't have to keep changing it. It says if I'm on ARM, then use this particular command to reduce the pinging on the cache line, things like that. It's very important. Yeah.
It is interesting though that it's const expr, which means it has to be generalized a little bit or tuned to a specific architecture or something, right?
Right.
Okay.
Because it doesn't work for a different architecture, right?
Well, no, but I mean, even between like an 8th gen i5 versus a 9th gen i5, right? That might change the cache line size, right?
That's right.
Okay.
Yeah.
Okay, next thing we have here is a new web tool, and this is build-bench.com. And Jason, you said this is put together by Fred Tingau, who we've had on the show before, right?
Yeah. So it's just like his quick bench to quickly test two different bits of code against each other. This one lets you quickly test the compile time differences between two different bits of code.
Right.
So if you're playing with different options.
Right.
Yeah.
So and the option or the example he has here, if you just go to the website, is a simple Hello World program, one using cease.io and one using IOStream, and it shows the pretty drastic difference between how long it takes to build the IOStream version. But you could toggle different settings and try out more things in your little code samples there. It's pretty cool.
I was actually really curious about this specific example, so I commented out the body of main. And it turns out that the entire compile time difference is just in processing IOStream header file. You don't have to actually use it.
Yeah. So compile time differences has not always been the most popular thing people was looking at. It was always runtime differences, but more recently, compile time has reemerged as the big candidate. And indeed, this is why. We have modules, right? In order to try to reduce the constant compilation problem, where every time you touch some include file, this is the second biggest problem in C++. The first biggest problem in C++ was the error novel problem, as you guys know, and that's what concept solves, right? So it doesn't give you the error novel on every template instantiation. The constant recompilation problem has always been an issue, and now with modules, theoretically, that can bring it down to a more constant time. And having some sort of benchmark that can allow you to be able to test that is extremely important. And it's definitely a welcome component for C++, I think.
Yeah, definitely. Okay, and then the last thing we have is a post on Bartek's coding blog. And this is about polymorphic allocators, which is a C++ 17 feature that I don't think we've really talked about on the show before, right, Jason?
It was briefly mentioned when, a little bit of a timeline here, if you don't mind. It was briefly mentioned when we had John Lakos on.
Okay.
And he mentioned a talk from some of his colleagues, Alistair Meredith and Pablo, I can't remember his last name.
Pablo Halpern. They're all good friends of mine. John and Pablo and Alistair Meredith, they're all good friends of mine.
So he mentioned a talk from them from CppCon from last year, which I went and watched, and that inspired me to make a C++ Weekly episode, which then he caught on his blog here and mentions my C++ Weekly episode, and then does a little bit more of a digging into PMR. Right.
So PMR is an important C++ 17 feature, and I imagine it's going to get even more important. Polymorphic memory allocation is a key component that can control the growth and the regrowth of things like std vector.
Yeah.
And I talked about early on that in the self-driving car domain, one of the things that the requirement for using dynamic memory after the car engine has started is that you've got to be able to use a memory allocator that is guaranteed to not throw exceptions, that is safe, that will not fragment. Well, this is something that polymorphic allocators can serve. Okay, instead of the standard allocator that C++ offers you, and this is why I think it's an important addition. I've actually talked to John directly about how we can make an allocator that fits the self-driving car domain. And he's actually promised me that this actually can work. I mean, although I have to examine it closely, I think there's definitely usability there to give you something that is a safe allocator. Okay. Ultimately, at some point, memory allocation is always been the big crux of the problem for real-time safety critical code. Things that you use in a self-driving car, things that you use in a pacemaker, things that you use that are medical or safety, extremely safety critical systems. It's the fact that memory allocation is non-deterministic. You don't know when it might fail. You don't know when it might suddenly take too long. Okay, you don't because of fragmentation. These are critical issues, and in a way, exception handling. The whole problem with exception handling, well, one of the problems, not the only problem, is because it seeks memory allocation during the exceptions.
Right.
For the exception object and the hierarchies and all that stuff, and solving memory allocation is critical in the safety domain for both just memory allocation itself and the issue with exception handlings.
So one thing I noticed, which is off topic from this particular article, but on topic from what you just said, is my understanding, at least from what I've seen so far, is that none of the standard container member functions are, let's say, like pushback, is not conditionally no except on whether or not the allocator would throw an exception. And it seems like that's a hole for what you would need to prove to say that, no, we know that we can safely use this standard container with this memory allocator because we know the memory allocator is no except, and that propagates through to the container.
Yeah, we would like them to be no except. Yeah.
Okay.
Yeah, we would like them to be, but they're not.
Right.
So there's no easy way around it. This obviously is suitable for a very specific domain, and we might have to. There's been talk about creating a safety version of the C++ standard library. Okay. Because right now it's not specifically for that in some ways. It's good for performance, okay, but it might not be the best for safety critical, but it can be if we set our mind to doing something like that. Okay.
Right.
Okay. All right. So, Michael, we had Gordon Brown on maybe 2 years ago talking to us about SYCL. Could you start off by reminding our listeners of what SYCL is?
Right. So SYCL is part of the Khronos portfolio of open specifications and belongs in the parallel computing group. It's a single source C++ parallel programming language that takes standard ISO C++ applications like even TensorFlow and then compiles them with a whole CPU compiler and a device SYCL compiler to generate code for many kinds of devices. In a more simple way, let's just put it this way. ISO C++ doesn't support GPU programming or heterogeneous programming directly. What SYCL does is takes ISO C++, adds the heterogeneous programming layer right now, today, and then makes it possible for you to dispatch to GPUs, to artificial intelligent machine learning devices that are being used in self-driving cars, for FPGAs, for DSP, for any kind of offloaded devices. So that's really the only, forget the words I said, they're important words, but at the end of the day, it's really just about making ISO going towards a direction which we think ISO wants to go anyway. And certainly there's a large group of us within ISO who are slowly driving ISO towards C++, towards that direction. But the reason they don't have it yet is because it takes about 10 years probably to get that done properly, because there's a lot of legacy code, millions of lines of code that might not care about heterogeneous or GPU programming, or they might in the future, but not yet. So we have to make sure that it works within that whole framework so that the memory model, the data model, the concurrency model works within the current framework.
So do you need to put pragmas or anything in the code or is it just kind of automagic?
Oh God, no, that is totally anathema to ISO. That is what Openmp does.
Right.
Openmp was a really great way of getting you to parallel and X-parallel and then heterogeneous acceleration by adding pragmas. Mm-hmm. I know because I was the CEO for about 5 years, and I actually led them through the transformation to accelerated programming. And we know that pragma The problem with Pragma, not other than your dislike of it, I can see your face grimacing every time I use that word. Totally understandable. Cool, guys. No worries. The real technical problem is that it does not allow you to separate concerns. In a single Pragma directive, you would encapsulate where you're going to do the offloading, how you plan to do the offloading, when you do it, in what manner of splitting the threads you're going to do it. It makes it very hard for in a C++ style to be able to say, wait a minute, I don't want to do it exactly like that. I want to do it this way. The other problem is, I used to write the Openmp compiler for IBM and added those things. The other problem I had a huge problem with was, and even today it's still not easy to solve, was where to put the error message. Because the Pragma directive encapsulates so much, but it often comes it often comes before the actual action, right? You have to set the directive, then you have to set the loop. You often can't figure out, well, which directive is enforced and what error message should I issue. So most of the time, we just give up on the error message. Don't say anything. I mean, that's just not going to fly, in a commercial system that has just can't give any reasonable error message. I mean, I'm not pulling Openmp. Openmp is fantastic, and it works over 3 programming languages, C, C++, and Fortran. But the problem with not being able to generate good error message wasn't totally pervasive. It was there for about 30% of the cases where it was hard to generate error messages, but it was enough to be bothersome. The other problem is how you can put a Pragma on a template argument. You can't. Can I make this template argument parallel? Well, you can't. You can't put it anywhere. There's no grammar space to put that in. So it is a difficult problem. But now we don't need that. SYCL can do it all in all natural C++. It looks just like C++.
Okay.
But we're not the only one. Many other programming languages have adapted to it. So while I really enjoy SYCL and I took over the leadership of it and the chairing of it, I also learned a lot from all the other programming languages that have come before us along the way to learn how to add heterogeneity to C++. HPX from Hartmut Kaiser does a great job of it, and it's pure C++. CUDA 8.9, the later CUDA, is much more adaptable to C++. Okay, the early ones were more C-like, but definitely the later ones are definitely more C++. NVIDIA has another thing called agency that does it. Beyond that, there's obviously Boost Compute, which is effectively adds a C++ layer on top of OpenGL. Okay. There is the U.S. national labs, CoCos and Raja. They have also done an admirable job of adding a framework on top of C++. So all these other languages have learned how to add heterogeneous programming to C++, along with SYCL. And they all have valuable learnings. And interestingly enough, they've all solved problems in similar ways. So I say it's time to add it to ISO, because it's not like we're digging for gold in Alaska here. We're not exploring Proxima Centauri. We are literally going through well-trodden ground. Okay, we know what we know where the problems lie, where the demons are. Most of it. I gave a LLVM keynote in 2018, where I said that the 4 major problems of heterogeneous computing is data movement, data locality, data affinity. It's just all data. And I forget the last one anyway, but you can look it up. But the point is that we now know where the problems are, and it's time for us to try to add it to C++. But that process will take time. But in the meantime, we have all these other languages that are available for you to try to use it. And of course, one of them is standardized across an open community of many companies, and that's what SYCL is. Sorry for the long-winded answer.
No, that's great. And on that note, is there already an ISO study group that is working towards standardizing something like SYCL into ISO?
So there is movement within ISO trying to add heterogeneous programming. In my keynote from LLVM 2018, I call it the quiet revolution. There's no official study group, but a lot of people are trying to help it along. And the reason is, this is not just the purview of any one study group. It crosses several study groups. It started when SG14 did a survey. SG14 is one of the groups I chair that has to do with low latency, but with games programming. The games programmers came back and says, we really would like you guys to add heterogeneous programming. Okay. And so from SG14, but because it's a lot of parallelism and concurrency, it landed a lot of features in SG1 as well as a library group. So I can delineate some of the efforts. So within SG1, we've opened up the specification to make it possible to add heterogeneous programming. Part of that has to do with fixing things like std thread, which only talks about heavyweight CPU threads, and changing that word to execution agents. By that change, by that very subtle change in the language, it means now you can add very, very lightweight threads that are typical GPU threads, okay? There were other things that has to do with forward progress that we had to change the language for. That was imperative for GPU, because GPUs typically have very weak forward progress, okay? Then we also did other things like add span and MD span through the library group, so that now you can have ways to talk about the data layout. Okay, it turns out that in GPU programming, it's extremely important to know how your data is laid out, because in CPU, you guys have all heard about contiguous layout. Things have to lay out contiguously. Well, that doesn't work when you in a GPU. Okay, GPUs do not like things contiguously because it's got thousands of threads working on it at the same time. So every thread that comes in needs to skip a certain amount of space. So that's why they call it coalesce. They actually have to be skipped. They have to have a certain span, and then they have to be recoalesced as a result. So this is one of the key things that has to do with the fact that you have to be able to control the data layout. I and my team are working on another aspect on data affinity, which is the ability that certain memory and agent have small affinity to each other. They could be closely placed or spread out. Okay, and that feature is working through SG1. Okay, so in order to make it all work, we can't just have one study group that does it. We kind of have to do it through everybody, and that's why I call it the quiet revolution. It's a revolution happening with a lot of people's help, but not any one single group controls it. And I actually like it that way. I don't want any one company or one group to dominate the design, because it turns out that everybody have good ideas.
Okay. So I believe you have an announcement to make about a new version of SYCL. Is that right?
Yes. So this is actually a great time to come to it. SYCL has been, so in 2018 at IWACO, which is the workshop for OpenCL in Oxford, we had SYCL 1.2 in 2015, and then SYCL 1.2.1 was released in 2017, and that was aligned with C++11. At the most recent online IWACO, which was also called SYCL Conference 2020, I unveiled a possible future roadmap of SYCL, where in 2020, we plan to release, and we did yesterday, July 1st, actually yesterday, June 30th, the first provisional SYCL 2020 release. That's going to be based on C++17. Because it's based on C++17, this means that we are enabling exciting C++ features like class template argument deduction and deduction guides. That makes code less verbose. There's also a number of great features, but the whole point is to make it simpler to write SYCL, to make it possible to work with things like very complicated templated applications like TensorFlow. Okay, that means that you can have things like specialization constants. It also means that SYCL, we now also have made it more generalized so that it doesn't purely depend on OpenCL. It still have OpenCL as a main component, but it now could certainly be ported to go on top of Vulkan or PTX or NVIDIA CUDA or any, as well as AMD's ROCm, so that it can be on any other kind of backends as well, because it's really just a language, a framework. It's really not anything specific to the back end. So that's why it's a huge thing. So yes, now you can download SYCL, the SYCL 2020 provisional at the Chronos website, and also give feedback at the Chronos community website channel. We're going to be going through about 2 or 3 months of review, public comment period, and then we will be going to final in September, aiming for supercomputing 2020. So that's a big thing, because we think that this makes SYCL much more usable, less verbose, simpler code, and more closely adapted to C++17.
My understanding is that there's multiple implementations of SYCL. Is that correct?
Yes.
Okay.
You can probably find any of my talks on SYCL 2020 online right now, but SYCL 2020 right now has about 4 or 5 implementations, all based on slightly different backends. And I can
Okay.
go through some of these with you guys.
Sure.
Part of it has to do with the fact that Intel recently really grasped onto SYCL because they were tapped to supply the next exascale supercomputer at Argonne National Lab.
Okay.
And they have developed an open source Clang compiler under their one API framework, and it is called Data Parallel C++. Okay, it's an open company collaboration. A lot of companies collaborate on it, but Intel has supplied a lion's share of the manpower at making it. And there's a lot of SYCL 2020 features that are already in there. Okay. The other one that I wanted to add is that CodePlay, obviously the company I work for, has a commercial implementation as well as a free download version that has various, so we have already implemented various forms of SYCL 20 within our compiler, and it's called Compute CPP. You guys mentioned Compute Suite. Compute CPP is the SYCL version. There's also, you mentioned Compute Aorta. That is actually the one that supports OpenCL. Okay. So Compute CPP is in use in things like the Renesas R car for self-driving cars, advanced driving assist systems, so as well as a number of other commercial implementations and industries. There is also Xilinx FPGA implementation, which was used to be based on Openmp. The backend actually uses Openmp constructs. So this shows you how. So you can see that, for some of these, it was based on OpenCL, but these other implementations showed us that we could easily make it work for other backends like Openmp, or later on you'll see ROCm. And so there's a guy at Xilinx named Renan Carriel. He's my editor for SYCL. He's done an amazing job in the last couple of weeks at making sure the spec goes out properly. And what they do is they're trying to make it work for FPGA, okay, which is an important segment coming up, I believe, in the mobile and edge device domain. Then there's also University of Heidelberg, a gentleman named Axel Alpe. I think he's a graduate student. And what he's doing is he's built something called HipSYCL, which was originally built for implementation that uses OpenMP for any CPU, CUDA for NVIDIA GPUs, and ROCm for AMD GPUs. So that was very, very useful. All these guys, all these implementers are on the call, on the working group call, which is like twice a week often. I also want to mention that Xilinx, yes, that adds to my other calls. So the one from Xilinx, I believe now has switched to the Clang base as well too, because of the work that Intel has done. So obviously the Clang one supports CPUs, multiple CPUs, GPUs, and FPGA through OpenCL with SPIR-V, and NVIDIA GPUs through CUDA. The CodePlay one, the Compute CPP one, can obviously support a host of GPUs, FPGAs. We tested on ARM and AMD devices, and specialized accelerators through OpenCL or with SPIR or SPIR-V, as well as NVIDIA GPUs through PTX ingested through OpenCL. And it's the first conforming implementation for SYCL 121. Khronos has this thing where, unlike C++, I suppose where they couldn't have a conformance test, Khronos has this conformance test you have to pass. And the compiler that passes this conformance test gets branded as being conformant to that specification. So we're going to do the same thing right now for SYCL 2020 to create a conformance test so that people can walk through. If you're familiar with spec CPU benchmarks, it's kind of like that. You have to get through that benchmark to be conformant, and the same thing happens here. So the Xilinx one is called Tricycle, and it used to use an OpenMP backend for any CPU and OpenCL with SPIR LLVM for Xilinx FPGAs. But I believe, don't quote me on that, but I think it's heading towards Clang for the using the Intel Clang distribution as well. So yeah, this is good as an ecosystem growth because it's like C++, right? C++ has GCC, has Clang, And it used to have a lot more distributions. That has actually gone kind of bad, that a lot of distributions are getting back to just Clang.
Yeah.
Right? But at least there's still GCC to keep Clang honest. And honestly, both of them have done each other good. Before then, and I was deeply involved in it, there was the Sun compiler, the Microsoft compiler, the XL compiler, and of course the EDG compiler. I think HP used the EDG and Intel used EDG. So really, way back when, before it consolidated to basically only 3 compilers, there was basically about 7 compilers that compiles C++. So SYCL is the language. It's like C++. And these implementations, Compute CPP, Intel's DP C++, Xilinx, and Heidelberg, is like GCC, Clang, XL, Sun, the EDG compilers. So that's in the C++ domain. We now are down essentially to 3 major compilers, right? Mm-hmm. Most of the other compilers have mostly folded to these 3.
Right.
I'm actually not a fan of that direction myself.
I think EDG is still being used in the IDE for Visual Studio, so that's.
I believe so.
Yes.
So yes. It is at least one. Maybe there's 4, but yeah. It is a yeah.
Yeah, Visual Studio is still kind of unique in that it's still a surviving standalone, its own implementation. It hasn't gone totally to Clang, although I think they're using Clang for the expression evaluator for the debugger.
I don't know.
They're definitely doing a lot of Clang integration. I know that. Yeah. So
I'm curious, because you mentioned Xilinx and FPGAs a couple times. Is the goal to make it so that SYCL C++ code actually compiles into hardware effectively?
So I'm not an FPGA expert, so I can't really speak too intelligently about that. I'm going to punt all those questions to my friends at Xilinx, Renan Carrier, as well as my friends at Intel Altera, who like Mike Kinsner, who's actually before Altera joined with Intel and all that. So these are 2 major FPGA vendors that are in the SYCL group. Right. Who are potentially working hard now at the supercomputing last year. There was a major paper by a couple of the Altera people showing how to use SYCL in an FPGA format. So honestly, I don't know whether it's trying to push it into a Verilog or VHDL or directly to hardware. I actually think it's mostly through SPIR-V to the hardware. So I think it's a shortcut to prevent you to having to use Verilog and VHDL which takes days and days to compile.
Right.
So I actually think that's the way it's going.
We actually recently had a talk at my meetup about FPGA development and C++, and the speaker and others made the argument that C++ when we're programming, generally thinking, we think linear flow. Hardware is inherently parallel, and therefore those 2 things don't map together. But now I'm just hypothesizing here, thinking, if SYCL, you're thinking effectively inherently parallel, right? Because that's the point, is that you can offload it to a massively parallel GPU. Then maybe that makes that mapping easier.
It could be, yeah. Mm-hmm.
I wonder if that's what they're doing. Maybe we'll have to get someone on.
CppCast with my friends from Altera and Xilinx. Maybe I'll explore this area.
Yeah.
Okay.
Can we talk more about just some examples of, what kinds of workloads, what kinds of applications benefit the most from something like SYCL?
Right. So typically, with CodePlay's implementation, we focus a lot on specific vendors, GPUs, or things that they want to put out in about 2 or 3 years' time, and they want us to build a specialized tool chain for those GPUs or AI processors. And lately, it's obviously focused a lot more into the type of processors that goes into self-driving car, like the Renesas R car. But Intel, with CodePlay, has now focused a lot of their efforts on making this workload now work in a high-performance computing domain. And interestingly enough, high-performance computing and the machine learning AI domain is very similar, actually. And so what happens there is that SYCL is being taken to be tested on all the computational fluid dynamics, quantum chromodynamics workload that the typical supercomputing center and applications do for things like weather forecasting, genome calculations, mapping, to atomic pile safety calculations, which requires massive GPUs. So the typical supercomputing clusters now are essential that is aiming for exascale computing, are essentially thousands and thousands of CPU with thousands and millions of GPUs.
Wow.
The next three supercomputing that is coming online, the first one is called Aurora, and it has essentially Intel Xe CPU processors with Intel GPU processors. And so what do you program that with? Well, you can either use Openmp, right, if it's C or Fortran. But if it's a heavy C++ workload, you probably don't want to use Openmp. Openmp has C++ support capability for acceleration to GPU, but it's not that great from a C++ centric point of view, right? Especially if it has a lot of templates.
Right.
So they chosen SYCL. Okay.
Mm-hmm.
And it's a good reason because they can participate in the open development of SYCL. It's wide open. It's part of the Kronos group. Intel is part of Kronos, so they joined the SYCL group. The SYCL group started out with something like 10 people, now has routinely 25 to 30 people calling in to listen to this. ANL, Argonne National Lab is there, and Intel, and obviously a whole bunch of other groups are there like Xilinx and Qualcomm, AMD, and obviously CodePlay, as well as a number of national labs and universities. But the point is that with that kind of workload, how do you program it in a standard way? Now, I don't know if you guys know about supercomputing evolutions in the last 10, 20, 30 years. I lived it for about 20 years when I was with IBM because we were trying hard to push through to the petaflop domain. That's 10 to the 15 floating point operations per second. Now, we've achieved that. In fact, the first computer to break petaflop was the Roadrunner, which uses a cell processor, which is also incidentally the same processor as in the PlayStation.
Right.
PlayStation, IBM, and Toshiba combined to create that specification. But it uses a computation model that is essentially using DMA access with a separate host and separate device code. And it was difficult, really hard to program. Now, the thing that you want to know is that with the DOE and the exascale computing workload, they tend to have very stable workloads that lives for 20, 30 years, code base that live for 20 or 30 years. But their machine is always the latest. Every 5 years, they buy a brand new machine. Okay, it used to be 30, 50 million, then it was 100 million, now it's $600 million. Yes, the U.S. government has a lot of money. Well, maybe not anymore after this whole thing. But the point of it is that they have the latest hardware to run these things. So what do they want? They don't want anything proprietary language. They don't want any proprietary language. They want an open language that is a standard language that lives for 20, 30 years, that they can at least have some say in how that language is developed. Okay? So that's why they love things like C++, general purpose language like standard C++, standard C, standard Fortran. Every DOE contract has those three listed right on the top. And as a vendor, you have to check mark every single one of them. Okay? So SYCL works in that domain because SYCL is an open standard language. So that's why they're looking at using SYCL to program these kinds of workloads. So I talked about two of them, which has to do with machine learning chips and HPC. There are other ones, obviously. There's also high-performance computing. I mentioned that. There's also FPGA, okay, embedded systems. SYCL is particularly good to work with things like embedded systems, as well as AI and machine learning chips like tensor processing units that are out there. So those are the kind of domains that SYCL can work in. We haven't gained leadership in every single one of those domains, but that's basically what the group is working towards. We've gained surprising leadership in the HPC domain, which is a very, very good win for us. But we're not resting on our laurels. We think that there's a lot more places for SYCL to go to.
I'm sorry, just to clarify, did you just say that there are specific processors that are just designed to run tensor workflows?
Oh yeah, that has been the big chip revolution in the last 3, 4, 5 years.
Okay.
Is because they've been looking at things they're called tensor processing units. They're loosely grouped as an AI ML processors, and what they are they optimize into machine hardware things like matrix calculations, because most of machine learning algorithm is nothing more than just a really giant regression algorithm that uses matrix calculations that does a lot of back and forward propagations across these matrices. So if you put those in hardware and then set the memory so that it works well with those constant retrievals of that little bits of data, it theoretically could make your tensor algorithm much faster than doing it all in software. So there are tensor processing units now in operations at Google, as well as a number of large other companies. Now, you and I can't actually buy these things mostly. Okay, so that's why most people aren't that aware of that, but totally understandable. But yeah, in that world where I live now, is the other part of my research is machine learning and AI. That's the other group that I lead in SG19 and ISO C++, is totally living there. I mean, to be honest, I honestly don't know if this is a really good solution, trying to build in hardware, all of these things. My life has never been has always been about the fact that general purpose language, when done right, can actually do a lot of these things much comparably, with a comparable speed to hardware. And indeed, that's one of C++ part of the direction group that I am. Their philosophy is that the generalized purpose language can build abstractions that are just as fast as any specialized hardware. Okay, and sometimes it takes a long period of time to prove that out. We're still trying to convince the embedded group people that C++ can be just as fast as C in the embedded domain. But it does take work, right? I mean, the fact that we think that many of these things can be done away with by a really good optimizing compiler, right?
Right.
So the same thing can happen in tensor in the machine learning domain as well too.
Since you just mentioned the ISO directions group, and in your bio you mentioned that you were one of the founding members of it, is there any news coming out of that group about the direction of C++ 2x 23? Yeah.
So I want to correct one thing. I'm not a founding member. I'm one of the originally invited members.
Oh, okay.
Although I am the chair, I'm chairing it this year, but it doesn't mean anything. We rotate the chairs every year to make it equitable and spread the load. So yeah, in a way, I guess you're right. I am part of the founding member. I was in the original founding group, but I just didn't want to make it sound that important. It isn't. So the C++ direction group was set. We think we were invited because we have been involved with C++ for a long time, and we think because we have shown particular impartiality in our work in C++. So the members there is obviously Bjarne Stroustrup, the inventor of C++. There's Howard Hinnon, who used to be a chair of the library working group. There is David Vandervoort. He is a vice president of EDG compilers. Mm-hmm. There's Roger Orr. He's been a long-time ISO committee member and the head of delegation for the UK. And I am there as well, representing, I guess I've been with C++ for over 25 years, almost 25 years now. I've put in a number of C++ 11, 14, 17 features, been chairing a number of different groups. So the direction group was trying to do something that was sorely needed, because what it was doing was that before this, believe it or not, C++ direction was more like a Ouija board. It was more like cloudy in motion, actually. You don't actually know where the molecules are going to go, because it could be entirely surprising the direction it takes, depending on who actually is present, who are the new people who just joined, who's particularly vocal, who's the loudest in the room. You guys, you know what happens in a lot of committees.
Yeah, we've seen this in the last and with C++ 20, where there was features that had wide support initially. Yeah. And then, depending on who showed up 3 meetings later, that feature is now removed from C++ 20.
What happened? We've been fortunate that it hasn't totally made C++ ineffective by this style of leadership. Part of the problem is it also lacks coherency, as you just pointed out, and lacks consistency. Okay, some features are not coherent with other features, and there's no consistency from feature to feature, or even within a single feature, as you said, it might be there one day and gone the next day. So we attempted to do that by writing a coherent document that lays out what direction we think C++ should go in the short term, which is next 1 to 3 years, in the medium term, 3 to 5, and then in the long term, 5 to 10 years, so that we can lay out what area we should focus on. It's especially important when we have over 200 people now attending, or at least we did before the shutdown, and some of them are brand new. And so we figured that it would be helpful for us to set directions for many of the new people, even the old hands, who can now understand this is the direction we want to focus on right now. And there's a document called P2000. You can do a wg21.link search on it, and you'll get the latest version of the document. That's another call I go on all the time, every 2 weeks. Is I have to call with the direction group and say, what's happening right now in C++? Is there anything we're concerned about? Are there features that needs more coherence, that are traveling separately through evolution and separately through library, but they're actually similar features, or they're dependent on each other features? So we really need to bring those groups together. So we talk about things like that. We talk about what direction we should set for C++ 20. What are the key likely features that we should put in and focus on for C++ 20? What are the features we should relegate to C++ 23? So in a way, we hope people listen to us. We don't make them listen to us. You can't, because every company is there, or people are there potentially for their own reasons or for their company's reasons. But we hope that by doing that, and maybe people respect that we actually have some history on this on C++, that we would be able to help narrow the focus of the committee, especially given the fact that there's so many people there. So have a look at the document P2000. I'm about to publish another iteration, the second iteration of it, so it's a pretty big document now. It's almost, I can't remember now, maybe 20 or 30 pages, but it does talk about what we would like to see in future C++. But it also talks about what process we would like to people to follow, given so many people are there. Part of that is because we think that the committee is, with its large number, is getting somewhat more fragmented, and we would like a more coherent attitude, a more friendly attitude between people. I was there when C++ was only 30 people, 40 people coming, and and you pretty much knew what everyone was working on. Nowadays, with 200 people, 21 study groups, most people don't know what someone else is working on. And we felt that there was a bit of lack of trust in the committee, that a colleague's work, and we're not trusting their expertise. So we wanted this document to assure people that, yes, you need to trust the process, the iterative process of the committee, where one group double checks the work of another group, they triple checks, and that's how the committee works. And you should not vote down something just because you yourself have not checked over the work personally.
Right.
That makes sense.
It won't work if everybody does that.
Right.
Right. Okay. Well, Michael, I feel like we could go on for a lot longer with all the stuff you've been working on. We'll definitely have to have you again on the show. Is there anything else you wanted to share before we let you go for today?
I'm really glad that this timely CppCast call has happened. I've been wanting to get on your call for a long, long time. I know I've seen the great work you guys have done, and I really admire the work you're doing at educating and spreading the C++ law. The only thing I wanted to close with to say is that SYCL 2020 is coming, and it's in provisional now, and it's going to be finalized later this year. We have a number of ways for people to help with the specification. Right now it's public, so you can go read it and get updates and can actually comment on it as you need. But you can also join as an advisory panel committee. Our advisory panel is large now. It's almost 10 people that have privy to the specification before the public. And they're all people from C++ and across the domain for heterogeneous computing. All the experts that I've known and worked with closely in the past. SYCL is all about creating cutting-edge, royalty-free, open standard for heterogeneous C++, for compute, for vision and inference acceleration and high-performance computing. So, and SYCL features are now available. Now, SYCL 2020 features are now available in Intel's DPC++ and CodePlay's Compute CPP. And we'll certainly encourage people to give us feedback or join the committee in one form or another to participate. Thank you very much, guys.
Sure.
Yeah, thank you so much for coming on the show.
Yeah, thanks
Cheers.
for coming on.
Cheers. And stay safe and healthy, everybody.
Thanks,
Yes.
you too.
Thanks, too.
Bye-bye.